So here's an interesting problem coming out of the geometric series section regarding present value. Consider Joe Schmo, star forward for the Canary Islands soccer team, signed a 6-year, $32 million contract. The owners of the team will pay him 6 equal payments, one per year, starting on signing day. The owners can earn 4% annual interest from their cash investments, say in a bank or something. How much does it actually cost the owners to pay Joe the $32 million? In other words, what is the present value of the $32 million contract? So let's think about that for a second. Let's say that you're the owner of the Canary Islands soccer team. You want to pay Joe Schmo $32 million over 6 years. You're going to pay him equal installments of 32 over 6. What's that? $5.33 million a year. You obviously don't need to invest or put into the bank, if you were to open an account, all $32 million to pay Joe, because you can earn 4% interest along the way. Something less than $32 million is how much it's going to cost you to pay Joe. And the question is, how much less? How much does it cost you to pay $32 million? That question is the same as, what is the present value of the $32 million contract? The reason they use that language, present value, is that let's say the owner of some other team wants to buy Joe from you. He's going to ask you, hey, how much is it going to cost you to pay Joe that $32 million contract? And you're going to say, right now, 6 years with 4% interest, it's going to cost me, $29.6 million. Oh, okay. Well, I'll pay you $29.6 million instead, and that's how much it's going to cost me to pay Joe that contract. So that's why they use the language present value. How much does it cost you right now to pay $32 million? Okay, so how do we go about doing this? The first thing we'll do is to define some variables. Bear in mind, what we're saying here is you're going to go to the bank with a lump sum. You're going to invest it in the bank, and you're going to pay Joe out of that account. And by the time that account by the time all the payments have been made, there'll be $0 left in that account. So it's sort of like the pay Joe Schmo account. All right, so let B sub n equal the balance of the pay Joe account after n payments. Notice I don't use n years. Payments is the key phrase. And then we're going to say let P equal the unknown initial investment. How much is in that bag of cash that you bring to the bank to say, hey, this is what it's going to take to pay Joe. This is the present value of the $32 million contract. All right, so in order to get the geometric series in hand, we should just start by writing a couple of the terms in the series. So let's say what B sub 0 is. Well, what's the balance in the account after 0 payments? Well, that's just P. That's the amount of money we put in. After 1 payment, which happens on signing day, that's just P minus, and we're going to say that's 32 over 6. I'm going to write it like that because I want to follow where this 32 and the 6 go. Okay? No interest has happened yet because this is signing day. This is the day. I'm not going to put the money in the bank well ahead of signing day. I'm gonna B sub 0 is happening maybe the day before signing day, and then B sub 1 is happening on signing day. B sub 2 is actually a year later, so I'm gonna have some interest. So how does this interest work? Well, I take the amount that's remaining in the account. I paid Joe for his first year on signing day, and then what remains for the whole first year is P minus 32 over 6. I'm going to multiply that by 1.04 because that amount earns interest for that whole year. And then a year after signing day is also when I have to pay Joe again for his second year's work. Okay, so I'm going to simplify this to P times 1.04 minus 32 over 6 times 1.04 minus 32 over 6. Okay, B sub 3. Well, B sub 3 is going to work a lot like B sub 2 did. I take the amount that was in the bank for the entire year, and it earns interest. P times 1.04 minus 32 over 6 times 1.04 minus 32 over 6. This whole amount earns interest. And then a year later, I have to pay Joe again. Okay, so then I've got this equaling the 1.04 is going to distribute to all three of these terms. So I have P times 1.04 squared minus 32 over 6 times 1.04 squared minus 32 over 6 times 1.04 minus 32 over 6. Okay, now I could go all the way to B sub 6, but I'm going to skip some steps here and see how that works. Okay, well, I see a pattern developing here, so rather than write B sub 4, B sub 5, and B sub 6, I think I'll just skip straight to B sub 6, because that's the goal, because there should be 6 payments made. So if you notice, after 3 payments, the exponent's 2, 2, 1, 0. So after 6 payments, this should be 1.04 to the 5th minus 32 sixths times 1.04 to the 5th minus 32 sixths times 1.04 to the 4th, and it's going to be minus all the way down to my last payment. Okay, and if you notice, I'll write this in here just for the time being. There's like a 1.04 to the 0th power right there. That's really just equal to 1. I'm just going to leave it there because it helps me count how many payments there are. Before I go any further, I want to make sure I'm not messing up. Do I have 6 occurrences of 32 sixths? I've got one with a 0th power here. That's the first one. Well, really the last one, but that's number 1. And then they'll have an exponent of 1, 2, 3, 4, and 5. So if I count 0, 1, 2, 3, 4, 5, I actually have 6 terms here that involve a 32 sixths, which means I have 6 payments of 32 sixths. That's good. All right. So 2 things have to happen now. First, we recognize that the balance of the account after 6 payments should be 0. There should be $0 left in the account after 6 payments. The second thing we recognize is that we have a geometric series somewhere on the right side of the equation. The geometric series happens to be right here. Notice that those 6 terms share a common factor of 1.04. But notice if I enclose that in parentheses and I have a subtraction sign outside, I have to change every single one of these minus signs into a plus sign. That helps me because I like thinking about geometric series with plus signs instead of minus signs. And the third thing I guess we need to pay attention to is that I want to call this the first term. I want to call this the 5th term. I want to call this the 6th term. So I'm just going to reorder things for myself to make the computation easier. So here we go. I have 0, because there's 0 money left in the account, is equal to P times 1.04 to the 5th power minus this geometric series. And I know that I can re-express a geometric series as a fraction. First term, 32 over 6 times 1 minus the common ratio, 1.04, common ratio to the nth power, which in this case is the sixth power because there are 6 terms, all over 1 minus the common ratio, 1.04. This is the trickiest part, I think, changing this geometric series into this fraction. Recognize that 32/6 is the first term. 1 minus r to the n. R is the easy part, 1.04. N represents the number of terms, and if you look the way I've written this down, there are clearly 6 terms. A lot of students look at this 5 right here and they think, oh, there are 5 terms. But if the first term has a 0th power exponent, and the last one has a 5th powered exponent, then there are 6 terms. And the denominator is 1 minus 1.04. And the goal here is to solve for p. So let's just solve for p. Let's just add this, well, let's think about it this way. If these two quantities, when subtracted, are 0, then they better be equal. P times 1.04 to the 5th better equal 32/6 times 1 minus 1.04 to the 6th over 1 minus 1.04. And then solving for p means dividing both sides by 1.04 to the 5th. And that just means putting a 1 minus, sorry, let me just write this out, 1 minus 1.04 to the 6th. Okay, that just means putting a 1.04 to the 5th down here in the denominator. 1.04 to the 5th times 1 minus 1.04. Okay, that's my solution for p. I'm going to use my calculator to figure. Okay, here comes the moment of truth. We're going to calculate how much money you need to bring to the bank to pay this contract off. So, we have a pretty complicated computation here. Let's think about how many parentheses we're going to need. 32 divided by 6, and then we're going to need to enclose this in parentheses, 1 minus 1.04 raised to the 6th. That's my numerator. Sorry, I believe I'm in some kind of fancy mode here. Turn that off. Okay, let's try this again. 32 divided by 6 times 1 minus 1.04 raised to the 6th. That's it. Okay. And I'm going to divide by a product of things, so I better put that product in parentheses. 1.04 raised to the 5th. Opening this second term, 1 minus 1.04. Close that term, and then close the product that is the denominator. I could also enclose the numerator in parentheses, but I don't need to because I understand the order of operations. That means 32/6 can be both separate from the entire calculation or be put into the numerator. Doesn't really matter. So enter. Okay, I need to put in 29.076 million approximately. So that's 29.076 million dollars is my initial investment. Let's just make sure I got that right. Roughly. Okay, so if I'm the owner of the team and I put in $29.0676 million initially, I will have enough money over the long run to pay Joe Schmo $32 million. So essentially, I'm saving about $3 million by paying him in 6 years. And if somebody came to me today and says, hey, how much is that contract worth? I'd say, it's worth $29 million roughly. So if you want to buy Joe Schmo's contract from me, you can buy it for $29 million. Okay, so it is worth generalizing this. I think somewhere inside me is a physicist who likes to take a specific problem and try to generalize and keep track of the parameters and assumptions. So I can make a general formula for the present value, so I don't have to walk through this process every time. I don't recommend that you memorize this. It's just maybe as a point of reference. Um, 32 represents the value of the contract overall, so I'm going to call that V. 6 is the term of the contract, which I'll call T. Um, then we have 1 minus, this is really 1 plus R, where R is the interest rate expressed as a decimal, to the T, all over 1 plus R to the T minus 1 times 1 minus 1 plus R. I think that's a good way of writing it. There's probably maybe a simpler way of writing it, but let me just write down my assumptions here. I said V is equal to the value of the contract. Not the present value, but how much it's worth at the end. T is the term. And that's it. And P is the unknown present value. The other thing that's worth noting here as a special assumption is that we did have first payment on signing day. So this formula is only going to really work when you pay the guy on first day. His first year comes on the first day, which is essentially saying that the payment comes before the interest. And that's not always going to be the case. All right. All right, I forgot to mention R, which is the interest rate expressed as a decimal. Yeah, so those are the three parameters, V, T, and R. And with those, you should be able to figure out any present value of a contract that involves the assumption where the first payment happens on signing day.